Good morning, everyone. I welcome you to our webinar today. I'm Yashima Jain, and I'll be moderating today's session for you. Our speaker today will demonstrate the features of Design Builder that can be used to incorporate active HVAC systems to simulate your energy efficient building. Before we begin, I would like to acknowledge the support of the Department of Science and Technology and the Ministry of New and Renewable Energy. I would also like to acknowledge the support of the sponsors and affiliates of Solar Decathlon India. Now, we once again have with us today PC Thomas. PC is the founding director of Team Catalyst and also an adjunct associate professor at the University of Sydney. He specializes in integrated building design, using simulation tools to assist in the design and delivery of sustainable buildings, in particular, in predicting the performance of mechanical services. He has a master's degree in mechanical engineering and over 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulation, energy auditing, energy efficiency in buildings, and solar energy. We welcome you today, PC.
Thank you, Nazim. So we have about an hour or hour and a half. So there's quite a few things to cover. So I'll get straight on it.
Sure.
If I can share my screen.
Yes. Yes, you can share your screen now. I've stopped sharing. Yeah.
Thank you. So please let me know if you can see it.
Yes, it's visible now.
Okay, perfect. So what I've done is for this lesson, I created a simple model. Okay, so there's a 3-floor building and each floor is divided to an east side and a west side. I put a partition in the middle. It's very simple, right? There is a ground floor, first floor, second floor, identical. Okay, and I haven't made many changes there. I've accepted many of the defaults in DesignBuilder. I've made some few changes. Okay, I've set the heating thermostat to 20. The default is 22, right? And I've made some changes to the power density, 12 watts per meter squared in terms of equipment. And also the lighting I've changed to power density and 5 watts a meter squared. Okay. Now, those of you who were here for the previous lesson, this shouldn't be a problem. If you have some difficulty with it, please review the previous video and then you will be able to get some of these answers. Yashima, I just want to check, you are recording this session as well, isn't it?
Yes.
Okay, thank you. All right. So what I'm going to do first is just show you some results that I've done, and then we'll get on to detailed HVAC. Okay. Now, when you open up DesignBuilder in its default state, it doesn't model a detailed air conditioning system. It models an ideal air conditioning system, a simple one, right? And what I will do is that using this simple one, I'll first show you some results that are generated, and then we'll move on to adding an HVAC system and going from there. So if I go to simulation and run the simulation, I'll get a series of outputs. Okay, and what I've done is I've made some runs and I've copied the results and renamed them here. So the first one I'm going to show you without the detailed HVAC, just using the simple one. I've got this one called Demo 00. Okay, so what I did is I save that, and I'm opening it up with the result viewer. I'd already saved some results, which is why I'm opening a file called the DRS. But you can see here what it's doing. Okay, so because I don't have a detailed HVAC system, it plots for me the thermal loads for the whole building. And what I've done is I've plotted here the cooling load and, in this case, the heating load. Now this is for Delhi, right? I have used a reasonably efficient envelope. So there's some insulation in the walls, there's some insulation in the roof. I'm using reasonably high performance windows. And what I can find is that there's very little heating required. And literally the heating energy demand is because there's air leakage through the facade. Otherwise, in an office building, I think I've got Monday to Friday, 7 o'clock to 6 p.m. There's hardly any heating required. If I look at some of the, warmer days, I guess, you can see here that this is how the cooling load is required by the building. You can see here the daytime temperatures are getting to be about 40, 44 degrees centigrade. At that point, our design day information has been exceeded. That the design day is around 42 degrees, if I remember right. And that means it actually will not be able to keep the building at 24 degrees. It'll go just above 24 degrees centigrade. That's normal, okay? There'll be a few days where you won't be able to meet your 24-degree condition, okay? The only other thing which is useful to note is that while the air temperature is very close to 24, your radiant temperature will be different, and that'll be a function of the building facade. I don't have any shading, so there's a fair bit of thermal energy in there. The radiant temperature is quite high, so what the people feel in that zone is going to be quite warm. And the similar sort of thing happens in the west zone as well. I've plotted in each case the middle level, so I don't have the impact from the roof. I don't have the mitigating impact from the floor. That's why I've done that, okay? So you can test things out like this, right? Now, let's now talk about how we can put an air conditioning system onto this building. Okay, so the first thing you need to do is to tell the model you want to do detailed HVAC. So if you go to model options, that's that little spanner on the top, the icons, and you move the slider for HVAC. I'll bring the dialog box across. So you can see here the HVAC is on simple. If you move the slider from simple to detailed, and for this case in the beginning, let's leave the data as being simple HVAC data. I'll show you when to move it to detailed HVAC data, which is available there. So once I say OK, you will find that you will get this extra thing on the left-hand side, which actually says HVAC system, okay? And if I click on that, it will come up with and ask me for what HVAC template should I try, okay? And the reason is DesignBuilder comes with a whole bunch of preset templates, and you can start by picking something close and then build from there. You can, if you don't want to use the template, you can cancel the template and you can add loops. So you can start by adding loops and going from there. But most of the time, it's better to add some template and work from there. Okay. So the simplest template for when you start is to use just a split system, which is the reverse cycle. So a heat pump split system. Okay. And Energy Plus has one. It's called this PTHP, Package Terminal Heat Pump. Okay. So if you add that, basically these are zone-based systems, right? And what it means is that every zone will have one of these systems available. Okay. So in each zone, it will go and add this split system. There'll be a cooling coil and a heating coil. And typically, which will be both running on a refrigerant cycle. And then there'll be an electric defrost coil, which of course in Delhi you won't need because we never get to temperatures much below zero and the coils don't generally freeze. Okay. And if I then say next, it will ask me which zones should be air conditioned using this system. And you can choose the zones that need to be air conditioned. And then if you click on finish, you will find that it has applied these systems to each of the zones. Now, the thing to remember, I'll show it to you here, is that you will now have two representations of each zone. Okay. One representation is what you already did, the geometric representation. So that's the one that tells you what constructions you're using, what's the schedule for occupancy of people and lights and equipment, what is the thermostat setting for each space, and all those things. Okay, that's your geometric representation. But you have the same zones. Okay, so 0, 0 east, 0, 0 west, which will be represented in the HVAC system. Okay, you mustn't get confused by that, right? And within that zone, again, you can edit at any level, and you'll find that as you get to each level, there are different things that are possible. Some of the things you should watch out for, there'll be a heating design supply temperature, there'll be a cooling design supply temperature. Those need to be the same between the two representations. Okay, it's a little bit confusing, but that's something you need to watch out for. So if I see here, it says here the supply air temperature for heating is 50, supply air temperature for cooling is 14. If I cancel that and go to the building level and look in the HVAC tab, then I should be able to go back there and have a look at the same supply air condition. So you can see here the supply air condition is different, right? So one of those you need to choose, and you probably need to choose to talk to an air conditioning engineer to find out what is the supply air temperature that you get for the kind of system that you're using. So what I'll do is for this exercise, I can put it to be the same as what I saw in the HVAC, the detailed HVAC tab. I'll put it as 50 and 14. And you may need to look at these humidity ratios as well, make them consistent, okay? Just remember that because you've put it at the building level doesn't mean that it will go down all the way if you've made any changes. So you can see here that I have obviously made some change somewhere, and because of that I'm not getting the same, I'm getting a different number here. So I've got to go back and make all these changes to make sure they're all the same, okay? I won't do that now, but before you do the runs, you will need to do that, okay? I want to show you a couple more things which you must be aware of, okay? So we looked at the zone group level. So you can see here, every zone is represented, and within the zone, you can see that it's got this PTHP system in there. If I double click, you know, I can go in there. As I said to you before, you can look at it at every level. We saw this level. If I go one more, I'll get to the actual system. And even within that system, I can go in there and look at things. So here's, I'm looking at the cooling coil here, and you can see I can edit things at each level. Be very careful. There's a lot of stuff around here. If you understand your mechanical systems, fine, go ahead and do that. But if you don't, leave them to be default as much as possible. The reason I wanted to show you this screen was that if you wanted to change the COP for cooling, this is the place you would do it, right? If you make a change at any one of these and you want to make sure you apply it to all the zones, make sure you go to target and then apply that change to all the zones. Okay, so if I make a change in the cooling coil COP, then I have to change that COP for all the coils. Otherwise, we get different COPs at different coils. Okay. Similarly, you can look at the heating as well. But there's one thing here that we haven't looked at. Okay, and if you look at this picture, you can sort of see where I'm coming from. The way this system is working, I recirculate air from the room. I either heat it or cool it. Most of the time I'm cooling it. And then I push it back into the room. Okay. I'm not supplying any outside air. Okay. The only outside air that's coming through in this instance is because of infiltration. Now, you may decide, and in most countries, it's illegal to build a system like that. You are supposed to put in some outside air. So what we can do is, in this case, for these zone-based systems, you may need to turn on these outside air, right? So if you go in here, sorry, I'll go into the system itself, and here you are. In this screen, you'll find there is an outdoor air supply. So if I click that box on, it'll ask you what size it should be. You can leave that because it will pick it up from the HVAC tab at the geometric representation. And then you just need to make sure you give the right schedule here. So we had a schedule 7 a.m. to 6 p.m. Monday to Friday, which I've given here. And this is pretty much all you need to do. A couple other things you may want to think about is, in most systems now, you allow the fan to run all the time, okay? And the compressor cycles on and off as required. And that's probably a good one to do. If you make those changes, make sure you apply it to all the zones. So all 6 of them should have that. And once you do that, you can run the analysis and you get some results. So what I've done is, because time was so short, I've already made all these changes. I've made the run and I've got some results. I'll show you the results here. So you can see here, I've got a PTHP output. Again, I'll show you this one. Now, it's something I didn't show you before, but I'll show you that in a second. So when I pick this up, it will do 2 things. It'll pick the ESO file, which has all of these results, and it'll also pick the summary file. Okay. So in the summary file, what I wanted to show you was that if you go to this report, the annual building utility performance summary report, it's a standard energy plus output, then you will get electricity for heating and cooling. So it now has included the part load performance of the coil and the fan, and it starts to give you energy use numbers for the fans, for the cooling, for the heating. Okay. Let me just close this. I think I've saved a file already with all these results. Let's see. Yes, I did. So here we are. So what I did is I plotted some numbers for the PTHP. And what I've done here is, again, I've plotted the energy used by the cooling coil for the east and the west zones on the first floor. Okay. So now it's telling me how much energy the cooling coil is delivering in terms of watts. Again, this is thermal energy, but if I wanted electrical energy, that's available here as well. And the difference between the electrical and the thermal energy is actually the part load performance of the system, or the COP of the system, if you wish. So if I plotted on this graph the electrical energy, and then we looked at it a little bit more carefully, say, let's pick a spot here. So if you look at the west, you can see here the cooling coil rate is 46 kilowatts, almost 47 kilowatts, 46,966 watts. But the electrical energy being used is about 16.5 kilowatts. So that multiplier is the COP at that point, okay? And the COP varies depending on the outside air temperature, what's the load, what's the condenser air temperature, and a bunch of other things. So it's quite a complex relationship to do that. So that'll then start to give you all the electrical energies that you are looking for. What I've also done here is I've plotted some of the air temperatures as well, or the room temperatures. You can have a look at it again. And because it's not above your 42-degree design day temperature, you can see the mean air temperature is being held very close to 24, 23.99 in both the east zone and the west zone, no problem. But again, the radiant temperature is higher than that 24 degrees centigrade that you've been trying to get the room to. Okay. So any questions here before I move on to the next system?
So PC, as of now, I don't see we have any questions yet. We'll wait for a minute, maybe. If someone has a question, they can send that in. If not, then we can proceed.
See.
So everyone, if you have any questions, please do send in via the Q&A window. All right, I think let's move ahead,
Keep moving.
PC.
Okay.
Yeah.
Yeah. No worries. Okay. So now, one very popular system in India, which I'm sure you guys will come up against, will be the VRF type system, right? And the way a VRF system works is a little bit different from just a straightforward split. Okay, so suppose we load a VRF template. Now, there is only one VRF template, and it's very, unfortunately, it's very kind of cold country type VRF system. But we'll use that to start with. It gives you an easy way of developing the VRF systems. It says here VRF with HR, which is heat recovery, and DOAS, which is dedicated outside air system. Okay. So if I put that template, then it tells me that do I want to overwrite all the existing templates? Okay, and you can see what it looks like. It's got a outside condensing unit. It's got inside fan coil units, and in this case, both a cooling coil and a heating coil and a fan. And because it's using a dedicated outside air system, there is an AHU, a fan system. Because it's designed for cold countries, there's a heating coil in there, and it puts in warmer air into the space, and then the system works. Okay, so we're going to overwrite the previous system, and to kind of change it to the way that we would normally use VRF systems in India, we don't need this full air system, right? This AHU we can delete, which I've done. Okay, and we can also, within the zone, we can remove the input and the extract from the AHU. If we don't do that, then sometimes, well, the model will get confused and it won't run. Okay, so if I go back and look at it from the HVAC system, you can see what's happening here. There's one outdoor unit, and there will be 6 indoor units, and they'll be connected to that one outdoor unit. Okay. Now, it doesn't mean that you have to keep it like that. If you decide that you want more than one outdoor unit, you can clone that outdoor unit, and then you can connect it to different zones. So you, for example, you can think of having one outdoor unit for the ground floor, one for the first floor, one for the second floor, or you can have one outdoor unit which does all the east zones and another one that does all the west zones. Any way that you want to do it. So for example, if you wanted to do something like that, what you would do is add a new zone group, okay, first, and then connect them separately to the different VRF units. You clone this one, and you clone this one, and then can do that, right? Again, it takes a little bit of practice, and there's a little bit of frustration doing the connections and so on. But once you master it, it's pretty okay. It'll go well. I'm not going to do that here. I'll do another more complicated system. I want to try and save the time for that. But what I did is I ran a simulation for a a VRF. And again, the one other thing that you may want to do before you run is to make sure you have included the outside air component for this as well. So if you right click at this level, you can switch on the outside air supply as before, change the schedule for when the system runs to something that's correct. So I'm changing all of these two schedules to the 7 to 18 Monday type system, and then make sure you put that to all the systems that you want to do that for. And if you look at it now, you can see you've got, I'll go back up to that zone. So you can see that within that zone, it is recirculating air as well as it's bringing in outside air and exhausting whatever outside air it brings. Okay. Now, in each country, there will be some code or standard which will set up how much you need to bring in terms of fresh air per person. Typically in Australia, it's about 10 liters per second per person. I believe in India, it's a bit less. It's around 5.5 liters per second per person. That's something you can speak to your mechanical engineer about. And where you include that is, I'm now at the building level on the activity tab. And if you go down the activity tab, you can see here minimum fresh air, and that's where you change it. Okay. And make sure it applies to all the zones. So that's where you can see the numbers. Now I've done all of those things, and I've done a run and got some results. So results will be very similar to the previous run. The only thing that you get, sorry, where's my, here we go. So I've got this. So what I've done is I've used one outdoor unit and I've put the 6 VRFs together. Okay. So what I did do though is to show you, I've plotted the values for the indoor unit. So this is the east side indoor unit on the first floor. And I've also plotted the cooling rate for the outdoor unit. So because the outdoor unit is handling all 6 zones, you can see that the energy that it's having to generate is much more than the energy for the east coil alone. Okay. And obviously, if you want to get the electrical energy, if you search through, you can find the electrical energy for the outdoor air units. It's a matter of looking through the all the variables that are being plotted, and you can see here there is a bunch of variables that are there for the outdoor unit. So if I wanted to find the cooling electric power, then I could plot it here. And the difference between the green line and this new line that's just coming up, this purple line, that's the COP at each point. So again, it varies depending on what's happening. Outside air temperature, indoor temperature, how much load, all those things are taken into account. So looking at the outdoor rate, now that's using about, it's delivering 28 kilowatts, sorry, 282 kilowatts of cooling energy for the whole building, and it's using about 93 kilowatts of energy. Okay. So you can do all those kinds of numbers. If you look at the summary table, then again, you'll find those numbers here. So total cooling energy across the year, about 112,000 kilowatt hours. Fans are all the fans are using about 20,000, 19,298 something kilowatt hours. And you can see here, the heating is quite small. As I said, the heating is quite small because we are using a reasonable, efficient envelope. In reality, if you have an uninsulated envelope, then the heating energy will be significantly higher. And if you have a fairly leaky envelope, then the heating energy will be even higher. Okay. So I won't bother going into too much more detail, but it will be available for you if you need to look at some of that. So I've showed you two fairly simpler systems, I guess. I'll show you one other system. I haven't managed to I wasn't able to complete developing it, and it doesn't run as yet, but it'll give you an idea. One of the systems that I believe you guys were all interested in was a radiant system, right? And radiant systems are really quite complex to model. So I'll show you a kind of a final configuration for when you've done the whole thing. In this case, you can see that I've got the zone here. This is the zone that I want to condition. There is a radiant, or in this case, I think I've got pipes in the concrete for providing the radiant cooling. And you've got an air handler that's going to put tempered air, dehumidified air into the space. So there's a dedicated outside air system with the AHU. And what you can see here is that I've got one cooling coil in the air handling unit. I've got a dehumidifier here, so that helps to this is a heat recovery system actually. So it's a wheel with a heat recovery system. The cooling coil, I've put a controller here which tries to maintain 50% RH, okay? And that air is sent into the space, and then the chill ceiling adds as much cooling as is required in the space. Now, you do need to worry about dew point control, because if the relative humidity in the space is too high, then you'll get condensation on the ceiling. So there some controls are there. That becomes somewhat complicated. You've got to start thinking about, you may have to test a few runs until you get to the right outcome, okay? And the way this is set up, it's quite a simple setup. I've got one chilled water loop that is feeding the cooling coil inside the dedicated outside air system. And I've got a separate chiller here, which is feeding the chilled ceiling. And the reason is, of course, if you read up literature in radiant systems, you'll find that the radiant systems need to be given water at a much higher temperature than the outside air system. The outside air system needs to be able to dehumidify, so it'll probably need the cooling coil to be at 6 degrees centigrade. That's the way that you might be able to dehumidify, okay? The chill ceiling or the radiant panel may need chilled water at a much higher temperature, 13, 14, 15, whatever your design condition is, and quite a small delta T, probably 3 degrees or 4 degrees delta T. So if you put in water at 13 degrees, then you may take out water at 17 degrees centigrade, okay? And what that does is, of course, it makes this chiller very efficient, looks very efficient, right? Uses very little energy. But be careful that you select the right kind of chiller. Not all chillers can provide such high temperature water. They may fail on high head, as it's called. Some of the modern chillers will do that. But the other way is that you put a heat exchanger in this loop, and then from the heat exchanger, you supply the chill sealing, okay? And the heat exchanger then allows the 6-degree water to change temperature to 13 degrees or whatever it is you want, and then go from there. So there'll be a separate pump in there. I haven't shown you that, but that's, if you search the internet, you see designs and talk to your mechanical engineer, there will be some options there. Now, both of these are water-cooled chillers, so they are being cooled, in this case, by a single cooling tower. The condenser side of the chillers are connected here, and and this chiller also, condenser side, is connected over there, okay? And there's controllers everywhere for each of these loops, and setting them up to be consistent is half the battle when you try and do a system like that. As I said, I've not had the opportunity to do a system like that, so I haven't been able to complete the demo system that I wanted to do for you. However, I'll show you as much as I've managed to do so far, and we'll do something a little bit more simple. Well, not simple, but I'll do another one which we can use many of the defaults to run it, to show you how to connect components and to set up things and so on. So in this case, what I had done was, when it loads up, yep. So here's my HVAC system. I've done what I showed you on that slide. I've got 2 chilled water loops. So there's a chilled water loop that supplies the dedicated outside air system. And within that system, on the supply side, there's a chiller, there's a pump, there's a set point manager, and then you need to set up things for that. There is another chill water system. That one is supplying the chill beams. And if you look over here, it's fairly similar. The only thing different is that this set point manager is doing something quite different. That's for the loop, sorry. If I go to the set point manager. Okay, so here I've asked it, oh, this is probably why it isn't running. Okay, you need to set this loop up so that it's scheduled to provide you with a higher temperature chilled water system. So suppose I can probably say 12 degrees centigrade. There's a default schedule here which does 12 degrees centigrade. So I can do that, okay? So this chilled water system will always supply the ceiling at 12. Okay. So those are the kind of things you need to look at. You will see that I've got an air loop. This is my DOAS loop, or dedicated outside air loop. I've set up within the air handler. There we go. Within the air handler, I've set up a heat recovery system, and the heat recovery system will recover heat both for sensible and for latent. I've put some numbers in there. I've used a plate heat recovery system. You can also put in a rotary system. I've not put any economizers, so it doesn't take any additional air except the minimum fresh air. And I've got a schedule to run that. Okay. So those are the sort of things that you will need to do. I've got 2 fans, a supply fan and a return fan. If your supply air fan has got enough static and you don't need a return air fan, you can remove that by unticking that box. So if I do that, then I have only got 1 fan to do the whole work. Okay. Within the zone, here we go. I've got, if I pick one of the zones, you can see I've got 2 components. So there's a chilled ceiling component and there is a extract, supply and extract component. And if you edit that at each level and for each component, you have things that you can do. So what's your design condition? What's your flow rate of outside air? All of those things can be set up here. So you will need to set up a cooling schedule, as well as you will need to tell the system what all it's doing. And again, as I said, in each layer, you can set up what needs to be done. Okay. Now, I have turned on condensation control because you've got to manage condensation. And what I've said is that when the internal temperatures get to within 2 degrees of the dew point, then start switching off the internal beams, the radiant sealing. But if you don't do that, then you will get condensation on the ceiling. We're trying to avoid this by making sure that the air that we supply from the dedicated outside air system is dehumidified. So hopefully the dew point inside the space will never get close to the dew point of the air, but it doesn't always work. Okay, so depending on how much air you're bringing and how much cooling you're doing, those things need to be done. Now, as I said, I wasn't able to finish it, so it still doesn't run. I'll try and see if I can make it run and share the results with you when that does happen. Okay. Now, what I'd like to do, we've got about half an hour, 40 minutes left. So what I'll do is I'll put in a system and show you how to do some connections, because sometimes that's a little complicated. So I'm going to save this one and call it something different. So I'll put this as a, I'll put this to be a VAV system. That's an easy one to do. And we'll start with a template. And again, we've got a bunch of templates. So I'll pick one of the VAV templates. There's a VAV with reheat and a water-cooled chiller. So that's a fairly not that complicated a system. So I'll put that in here. And you can see what it's doing. I'll just accept that default for the present and overwrite the existing system. Okay. So if you think about it, the way the system is set up, right now you have one chiller, one cooling tower that cools the chiller. You have one boiler that provides heating. So the boiler provides heating to a heating coil inside the air handling unit. It also provides heating to the reheat coil within each zone. Okay, and typically in India, you don't have any heating in the zone side on the VAV box. So sometimes it doesn't control the temperature very well in winter. Okay. But this is a very traditional VAV type design. The only thing that's sort of non-traditional about it is that you always have more than one A handling. If I was going to do this in detail, I'd probably divide the flow plate up into north, east, west, south, and the center zone, and then I'd probably have air handlers which did each orientation and one which did the internal zone. But for the present, this is a pretty good sort of system. Okay. Now, this is all pre-connected, so you don't have to do very much indeed. But if you want to connect anything, then let's do one thing. I'll add another AHU, and I'll add another zone group, and I'll show you how we do that. And what we'll do is we'll keep all the east zones on one A handler, and all the west zones on the A handler. Okay. So before I do that, few things to just warn you about when you accept defaults. Unfortunately, I mean, the guys who write the software programs are not mechanical engineers or architects for that matter. They're programmers, and some of the defaults that they put in are not always relevant, right? So I'm going to look at each loop. So if I go into the chill water loop and I look at the loop, you can see a chiller, pump, set point manager. If I edit the chilled water loop, then, sorry, let me bring that up. Here we go. You can see that these defaults will not work for India and for Australia either. We don't use ethylene glycol, generally we use water. So that's the first one, okay? And most chilled water systems traditionally used to be constant flow, okay? Nowadays, there's a lot of variable flow primary systems, but those are difficult to control, and the flow differential is not a lot, not unless you are very, unless you're a really good engineer. I would be very careful with that. Now, this is also not very useful. Okay, the design exit temperature is 6 degrees centigrade. That's fine. Typically in India, they use the ASHRAE number, so you might see 6.67 or something like that. But metric, we use 6, and the design temperature differential is 6. So it means that the water goes in at 6, comes out at 12 on a design day. Okay, so when it's sized, it'll do that 6-12 sort of loop. Now I'll change the schedule to our 7 to 18, Monday to Friday. You can, if you want to, give it some lockout temperature so that when the temperature gets below a certain value, you cut out the chiller and then you bring it back in when the temperature reaches a particular level. For the present, I'm not going to do that, okay? Now, if you had more than one chiller, then this is where you would tell it how to run those chillers, what priority you can run those chillers at. So at the present, we've only got one chiller, so nothing to worry about. I'm going to leave it there, okay? So that's my chilled water loop. And what it's, if you want to look at it a bit more carefully, you can examine each of those things. If you look at the set point manager, typically it should allow water to go out at 6 degrees centigrade, which I think it does. Yep. So this is for all time. Anytime it works, it comes out at 6 degrees centigrade, right? You've got a pump, and you can set pump numbers. Again, I would say that this design head is very optimistic. You probably need 10 times that head, or maybe 150 kilopascals, 120 kilopascals, but certainly not 20 kilopascals. You pretty much never do that. But those are things you need to check with your mechanical engineer. Okay. So that's my chill water loop. Okay. If I look at my cooling tower, condenser water loop, again, it's worth just looking at it. So the condenser loop connects to the condenser side of the chiller, and it has also got a pump, and it's got a set point manager. So it's worth looking at how the loop is set up, and if there are things that you don't like, you can change that. Okay. So typically, the one thing that you do need to change is your schedule that it operates in. So if you wanted a 7 to 18, you can do that. You can decide to follow the chiller's operation with outside temperature if you wanted to. That's something you can do. You can leave in most condenser water loops, engineers don't like to see a variable flow because the chiller needs to get cooling. If you don't provide the chiller the right amount of cooling, you may cause the chiller to go to fault, and that's a much more dangerous thing to do, than just save a few kilowatt hours on variable flow. But that's something, again, you can talk to your mechanical engineer. Now, what I'm talking to you about are practical aspects of air conditioning systems. Almost nobody will talk about that when they do simulation. They'll just pick the easiest way, and it will show fantastic energy savings, but you will never be able to realize that in reality. Anyway, let's leave it at that. You can look at each of those components. So if you went to just the cooling tower and you had a look, there are things in there that you may wish to change. Again, you may need to speak to an engineer who knows some of these numbers and put in things that you may want to do. At this point, I'm going to leave it as a simple single speed cooling tower with the fan cycling. Okay. In the entire simulation package, in all simulation softwares, the cooling tower is pretty much the worst model we have. For some reason, there's been very little research done on cooling towers. It's quite a complex beast. There's evaporation going on, and it's quite difficult to model it. So in what we've done in measurements of practical outcomes, they're never the best represented. So make the cooling tower model as simple as possible, and you get pretty decent results. Okay, now again, the pump, I would suggest that even here the pump head is pretty small. 20 kilopascals is really pretty small. I will change it to 200, but 200 is probably a little too high. You can find something better than that. Talk to your mechanical engineer and figure out what's the best, and that'll leave it going. Your set point manager for cooling towers, here you go. This is an interesting one. So what it's doing is it's following the outside air wet bulb temperature and then trying to be about 1.5 degrees away from that. Again, that's pretty optimistic. I think once 2 or 3 degrees between the outdoor wet bulb temperature and is about as much as you can get to. And this minimum set point temperature is extremely optimistic. If you were doing 10 degrees, you're expecting the offset temperature to be 13 degrees. And at that point, you don't need a chiller. You need something to heat the system with. So I would say, you never really want to get below 20 degrees. And many of the chillers will not allow you to get down below that as well. So these are things that you need to maybe speak to a experienced mechanical engineer to do some of those things. Okay, I won't bother with anything else for the present. I think, let me just see what the air loop's doing. So here's my air loop. Okay, so because we're a VAV system, we can actually use something called warmest. And what that means is that it'll try and pick a temperature that gives it just enough cooling to keep the space under conditions. Okay, so I'll leave that for the present and go from there. Now, if I did a run, and I can probably do that. Let's see, time's not too bad. Then here we go. So yeah, let me just do 1 month so you can see it'll go pretty quick. And the so first it does an auto sizing, and then it runs the simulation. Okay, so I'm just going to cancel the results because all of the results will be in the Energy Plus folder. And they're there. So if I double click on the ESO file, it will load those results. So here's my HTML file results. And you can see here it's June, so there's obviously no heating. And for that 1 month, the chiller is using about 11,500, 600 kilowatt hours. And the fans are using about 10,000 kilowatt hours. The pumps are using about 2,000 kilowatt hours. The cooling tower is using about 1,000 kilowatt hours. Okay. So those are numbers that come here. You can obviously look at any of those numbers over here. Okay. So excuse me. I just need to shut this off. Okay, sorry. So now you can see there are other things that are available in the ESO file. You can see all the chiller numbers, the AHU numbers from the cooling coils. So you can see, in this case, the chiller and the AHU number should be pretty much the same because there's only one AHU. It's picking up all of the loads. If I plot the two, they'll be pretty much on top of each other. There's a slight difference, but pretty much the same everywhere. And you can see all the other things that are happening, and you can plot any of these and find out what's going on. So if you wanted to look at the electrical loads, you could do that. So if you wanted to get what the chiller is using and what the cooling tower is using, electric fan for the, I'll just put that as power, it's the same. So you can see here the cooling tower fans use much less compared to the chiller compressor, which is what you expect. There will be a AHU supply fan, and I've got supply and extract fan. And you can see the fan actually will move up and down a little bit. Now this is a warm month, so there's not much. Here's a couple of days where you can see that the fan has also moved up and down because it's a variable air volume type fan in the VAV system. Okay, so you can see some of those results. You want to check that it is actually maintaining temperatures in the zones before you go forward, but that's the way to do this. So what I'll do in the last few 10-15 minutes is we'll do what we discussed, and that is that I will add a second AHU and a second zone group so that you guys can see how these connections work, and then we'll leave it at that. Okay, so once I'm on the HVAC system, I can pull the whole system up and down. What I want to do is to clone the HU and clone the system, sorry, the zone group. You remember what I said previously. You have a geometric representation and you have a HVAC representation for each group. Okay, so let me okay, so what I'm going to do is I've just selected the air loop. You can see all the red parts. Okay, and what I'm going to do is use this clone tab, or clone icon I should say, and the easiest way to do it is you click somewhere inside the HU and you get a clone of the HU, or rather the air loop, and then place it somewhere. So you've got the full air loop. You can see that exactly a copy of what I have previously. I will press escape and click somewhere else, and there's my clone of the AHU. In a similar way, if I click on the zone group, again it turns red, and then these icons light up, so I can do a clone of the zone group. So I'm going to click that inside somewhere, bring the zone group back down here somewhere, click once, and then press escape. Okay, so now you can see that these two are not connected. I haven't got any connections between the coils and the chill water loop and the hot water loop. So I need to make all of those connections, right? And there are some stringent rules in how you make those connections. When I did the cloning, you can see here that I got an air loop 1 and a zone group 1. Okay, so what I'll do is if I go to zone group 1, as soon as I click on that, it says zones must be added to the zone group before you can navigate to it. Do you want to add some now? If I say yes, it will give me a list of zones, but there aren't any that are available because all of those zones in the model are actually connected to this zone. So what I'll do is I'll go to that first zone group and I will release some of these zones. Okay, so let's say I will release all the west facing zones. Okay, so the first zone group is actually an east zone group. So how about I rename this so that I don't get confused. So I'll call this zone group east. And you can see here that all the east facing zone groups are ticked in this box. So it's easy for me to see that. So now I'll go to the second zone group and I will incorporate all the west facing zone groups on that and call this a zone group west. Okay. So the AHU that I'm going to connect these two will have all the west and east zones separately. Okay. Now I just got to make sure that I've got the right ones. Yep, west there, and these are east. So that's done. Now you need to do a similar thing with the AHU, but first let's make some connections. Air loop that was already there is all connected. We know that it's the east ones, so I'll just rename that, call that east again, so I know what I'm doing. Okay, so I've got this is east. Now this one is what I need to connect. And the way you connect them is if you click on the demand side, it will show you what's possible to connect. Okay. And on the top here, you have plenums, supply plenum, splitters, and you have connectors. So I will use the connect components. And DesignBuilder is smart. It won't let you connect a supply to an exhaust. It just won't connect it. Okay. So I can go from here and connect that part. So these are like ducts that I'm connecting. Oh, sorry, yep. Here we go. And you can see green dots, so it'll show you the connections. So my air loop 1 is connected to the zone group. What I want to do is I will escape out of here. I will rename that to be west so I can see what I'm doing. Oops. Okay. So here we go. And it'll rename pretty much everything on that AHU as AHU West. Okay. Now I've got to connect all these coils because if the coils don't get supplied, then it won't know what it's doing. So in the same way that we did for the air loop, you can go to the chilled water loop. And again, if you click on the demand side, it will tell you what is possible to be connected. So here's my chilled water loop. And you can see here there are some open connections. Every time you add a new coil, it will give one more connection. So you never run out of connections. Okay. So again, you've got a coil connector when you're at this level. So you click on that and you can draw anywhere. I mean, really, it's only for you to understand the drawing. You can draw the lines one on top of each other and it doesn't really care, right? You just need to be aware of what it is that you are drawing. So, but just to make it a little simple for us, I will make a connection here. Okay. So I've connected that chilled water coil. That's all I need to do for the chilled water loop. But I also need to connect the boiler and the heating coil. Okay, there are two heating coils to connect. If I go to the chilled water loop, sorry, the hot water loop, what am I saying? Apologize. Then same sort of thing. It will show me, if I go to the demand side, it will show me what connections are available. You can see here, right? Again, I've got a connector, so I'll quickly do those up. Let me go here first. This one. Oops, sorry. Here we go. Oops. And as I said, it's really for you to see. And if I connect it there, as soon as I connect it, you get an additional connecting point. So I'll go one more. And the dark one goes to the inside there. and this one, there we go. Okay, so now all set. Now, because I cloned everything, my control strategy for each AHU will be exactly the same. The set point manager would have been cloned, so it knows what it's doing. It's doing the same sort of control as the other AHU. When it needs to do that control will differ, because the east zone will see a higher load in the morning, west zone will see a higher load in the afternoon. But because it's a big flow plate and I've just divided up into two, that difference won't be so much, okay? In reality, you should have a 4-meter wide east zone, a 4-meter wide west zone, a 4-meter wide north zone, and south zone and center zone. Then you can connect different HUs and controllers together, and then you'll see a big difference in the way they are doing. But for the present, this will do. If I save this, I will just rename that, call that 4, and instead of DOAS and radian, I'll just call it VAV so I know what I'm doing. Okay. Again, let's just run June because it's a very quick run, but typically you want to run the whole year. So here we are. I'm not going to do daily. I'm just going to do monthly and hourly. And it will do, as I said before, it'll do sizing calculation first, and then it'll run the simulation. Okay. And you need to set up the sizing calculations so it does that correctly. Again, I won't load the results here. If I go straight to the folders and the Energy Plus folder, that result is here. And if I look at the summary, again, you can see cooling is 11,000 something. It's come down a little bit because now I've got 2 AHUs and it's able to control it a little bit. Fans have gone up a little bit because now you've got 2 AHUs and fans. The pumps and heat rejection won't change very much. You're still dealing with the same amount of load, okay? Old engineers will tell you, including myself, that load is load and you have to deal with the load. How you deal with it, you know, sometimes it's a bit more efficient, sometimes it's a little bit less efficient, but there it is. So here's the chiller cooling load, and now you have 2 different cooling coils. So if I add those 2 together, you can see that there will be slight differences. If you look at them, you can sort of see that the west cooling coil will call for a higher load in the afternoon. You can see it's calling for just a little bit higher. And the east one is calling for more cooling in the morning. So suppose I just pull this for 1 day so we can get the hours below. Here you are. So 7 a.m. in the morning, it starts up, and then first, both of them call for cooling, but the east one calls for a bit more. And then in the afternoon, the west one calls for a bit more. Okay. So it's doing what you expect it will do. If you add these 2 results, it'll be what the chiller is providing, or very close to what the chiller is providing. Okay. There's some losses, but very little. So that's, and you can, of course, plot any of these things that Energy Plus has generated. You can ask for more outputs before you run the simulation. If you go to the output tab and options tab and you check box other things, then it will load those variables as well. So we're almost kind of there, but I think I've managed to cover a fair bit in that time frame. If we have some questions, I guess I could respond to that.
Sure. So thank you, PC. We've had a couple of questions, so I'll take them one by one. The first question is how to take care the deration factor due to extended piping length and indoor temperature condition based on end user need.
Okay, I think I know what you're asking for. You're saying that if there's a long pipe length, you have some losses. How do you consider that? Okay. Now, if you go into the loops, can you still see my screen or?
No, your screen is not shared.
Not shared. Okay, let me have
Yeah.
a look here. There is a UA delta T which allows you to cater for some of that. I think it's in the loop side of the HVAC loop. Now, the derating factor for VRF systems is more difficult to play with, but the chill water system is maybe a little bit easier to deal with. Now, where exactly it is, I've got to think about. Okay, if you leave that with me, I'll try and find where it is that you have to meet that. But you can describe a UA delta T around the loop, and it will actually allow you to do that. Let me just have one more look and see if I can find it.
Sure.
If I can't, then I will. Okay. No, I can't see it straight away, but I'll try and find that and send that across.
Sure.
That's the way you would deal with that.
So another follow-up question is that also can you guide us on how to optimize circulation ratio for VRF selection?
Yeah, no, I can't. Ask your mechanical engineer. VRFs are, they're a pretty crazy sort of design. I'll give you some insights of what I think you need to think about when you do VRF selection. One of the things that is said about VRFs is that they're very efficient because they do what's called gas bypass. So, if you've got heating and cooling happening in the same building, then it will take the refrigerant gas from wherever the cooling is being required to the heating side and make it sort of more efficient. In reality, particularly in India, that hardly ever happens. You very rarely in summer have a situation where one part of the building is being cooled and another part of the building is being heated, right?
Yep.
So therefore this sort of ultra high efficiency of the VRF almost never really happens. I think even in Sydney, I did I think I did some numbers, and the number of hours was less than 200 hours across the year, where that sort of potential existed. And what it also demands is that if you really want to have a building where one side is being heated and one side is being cooled, it is asking you to design an inefficient building, and that's really not what you want to do, right? However, they are more efficient than normal split systems because typically you have more than one compressor, and one of the compressors will be an inverter compressor. So for the first 50% of capacity, the inverter compressor will have some variable speed potential, and therefore it will be a bit more efficient in that regard. Of course, that doesn't work unless you've got at least 2 compressors in there, and one of them is a variable speed compressor, inverter compressor as they call them. So for the smallest designs, VRFs and splits are pretty close to each other, right? Some of the newer Daikin systems, yes, they do give you small capacity systems with inverter compressors, and they can be quite efficient. Their efficiency, some of the things to watch out for is that you look at the condenser specifications, there will be a cutout temperature. So, it'll kind of tell you that if the ambient temperature goes above a certain point, then actually the system cannot produce any useful cooling, and the compressor might shut down. Okay, and unfortunately, due to global warming, we're sort of getting to the point where we're beginning to hit 45 degrees plus in some situations, and when that happens, some of these air-cooled condensers really struggle. Okay, so something to be very aware of. Is there a solution for that? I think people are beginning to recognize that water-cooled systems are useful during those times. But of course, when you have really hot temperatures is when you want to conserve water as well, and so it's not a panacea. It's not a silver bullet. So that's the time when evaporation's highest, and that's when you can use your evaporative coolers very well as well, because the air is very dry. So you will get quite efficient outcomes, but you lose a lot of water. Okay, so it's one or the other. The best thing to do is to try and build a building envelope which can try and remain as cool as possible without artificial cooling, and therefore you need the least amount of cooling to do that. So good daylighting, you can switch off electric lighting, good shading, insulated walls and roofs, and contact with the ground, because the ground is always much cooler. Those kind of things will drive the cooling load to be low, and then you need less capacity to deal with that. But VRFs are a really difficult system to design correctly. You can do it, any sort of VRF, and get some sort of cooling. Usually you'll find that they overcool the space in milder conditions, and people are very uncomfortable. They don't do dehumidification very well, so if it's humid, the system will not give you very nice conditions inside. But these are all sort of well-known problems.
Right. Thank you. We have another question about VRF, and I'm not sure if it's the same. So the question is how to optimize the combination ratio of VRF system selection. So is circulation ratio and combination ratio the same thing, or is it something different?
I think they probably mean the same thing.
Okay. All right. So that's all we have from the question side for today. We'll wait for a minute or so. If you have any questions, please send in through the Q&A window. So we'll wait for a minute for you to.
While we're waiting,
yes.
What I did with the the chilled water system, you can do exactly the same with the VRF system. So you can clone the outdoor units. So you can put a second outdoor unit like that. You can clone the indoor units by adding a second zone group. So you can select that, clone that, and then you can do exactly what I did previously, release some of the zones from one of the units, put it into the second zone group, connect the outdoor units to those indoor units. And then, so you, in a building, you can have more than one outdoor unit, and you can decide how you want to do that. Within the, I guess within the outdoor units itself, you can go in there, and there are quite a few settings that you can look at. And some of those things can be adjusted, and it will allow for some finer control when you do that. Okay, so you want to maybe look at some of those things. There is, you know, in each section there are bits that you can work on. So I would suggest definitely don't change the curves. The curves, there are, I believe, something in the order of 20 or 22 curves to describe the performance of a VRF system. They're built around the Dakin model because there was a student from Dakin who did his PhD, and that's the model that's in there. It's a pretty good model. I don't think there's any other model in the world that is as sophisticated as this one. But you can change the way the curves scale by looking at the, you know, changing the cooling COP, changing the heating COP, doing a few changes around the edges. But beyond that, I wouldn't do too much. Okay. There's a lot of help in the help file. Please do, you know, read that. There's a lot of help in the DO2 engineering manual. So for those of you who are mechanical engineers and want to learn about that, there's stuff in there. Just download the free DO2 manuals. I think there's a company called Big Ladder, and they have all the DO2 manuals online. So they're searchable, and you don't, you know, I think I can see Prasad knows about them. So I'm sure you'll find them for you if you need them. But that's probably as much as I would suggest.
Right. Prasad, you have your hand raised.
Yeah, sorry. I just wanted to check in with PC about the some of the demo systems that you started talking about. Is that, and you said that you might be able to give those. Is that the intent, to have something ready that the participants and the students here can use?
Look, I hadn't sort of thought about that, but if you want the demos that I did for the other systems, I'm happy to share them.
Sure.
They all run.
Okay.
They're not perfect, but they all run.
Okay.
The only problem that I had with the Radiance system that I haven't sorted out as yet is when you do a Radiance system, you've got to, the construction needs to change. There is, I mean, help available and you can find it. In the constructions, you've actually got to tell it that it's got an internal source. Because when you put cooling into the thermal mass, it needs to know that the mass is actually a provider of cooling, that there's an internal mass which is being cooled. That part I haven't managed to sort out because I've never really looked at it before. But there is documentation. The other systems I'm happy to send you. It's pretty straightforward. Yeah.
Okay. Anything else, Prasad?
No, that's it.
Right. And we have one more question, PC. How to take care of part load performance in chilled water systems?
Yeah. So because you're using the detailed HVAC systems, that is actually taken care of for you already. So if I'll just pick up the, let me pick up the chill water system. All the curves that are attached to chillers already look after the part load performance. Okay. So I'll just show you, and then there. If you go to the actual chiller object, it will show you the part load curves, and Energy Plus has, and DO2, of course. It originally came from DO2, and then the chiller objects came across to Energy Plus. They have very sophisticated chiller objects, probably the best in the world. So if you, what I've done is I've just clicked on the chiller, and you can see here that each chiller, you can, and there's a bunch of chillers already available within Energy Plus and DesignBuilder. If you know your rough capacity, you can pick a chiller that sort of matches. Okay, so 1,000 kilowatts, 2,000 kilowatts, there's a whole bunch of chillers here. But the default chiller, the DO2 centrifugal chiller, scales. So you can change the COP and it will scale. And you can see here that if you click on the, oh, I can't get it to do it here, but if you try to edit these chillers, you will find that each of the chillers has got a series of curves that are built in, right? And those built-in curves will do all the part load calculations for you. So yeah, there we go. So there are 3 sets of curves, okay? One has to do with capacity, one has to do with energy input ratio, one has to do with part load ratios. Those 3 curves, they provide a kind of a 3D surface, which the model is looking at all the time. So it's looking at your input temperature, your output temperature for the chilled water and the condenser water, and the part load performance or the part load capacity, and then it works out a COP at that instant. Okay, so every hour it's calculating the part load performance. That's a big difference between using the detailed HVAC model and using the simple model. Simple model, there's no part load performance. It just gives you the thermal energy that's required. And you can use a fixed COP and estimate what the electrical energy is. But when you use the detailed model, it does all the part load calculations for the fans, for the cooling tower, for the chillers, for everything, pumps, everything. And you've got a whole bunch of different curves for the fans. There's an Appendix G curve for all the variable volume fans. You should use those. They're probably the best thing that's available right now. Just remember, when you're modeling pumps and when you're modeling fans, you're not just modeling the fan or the pump. You're modeling the fan plus duct system. And no one's designed the duct system at the early stage. You only get that when the contractor comes in and he works out the lengths of the ducts and he finds the resistances. So you don't know what the resistance is. So we've got an average set of curves that ASHRAE is put out, which is these Appendix G curves. Okay.
Yep. Thank you, PC. So that's all from the questions side today, and I think we'll end the webinar now. So thank you so much, PC, for taking out the time and doing such a great session for our participants today. And I hope our participants will be able to make use of the knowledge and use the software more effectively. Thank you, everyone, for participating today. And we'll see you next week for our next set of webinars. Thank you.
Thank you and good luck.
Thanks, PC. Bye-bye.
Thank you.
Thanks.
Yep.
Bye-bye.
Bye.